I imagine you all might have questions about the practice test. Not that we have to do that, but
Kind of. I mean, I went to Dr. Koger's Hotstars, which is like an hour ago.
oh yeah,
So he basically went over like all of directional derivatives,
Okay.
and, like the 3 kinds of problems that really is.
cool.
So that was pretty helpful.
Yeah, that's super helpful. What kind of problems do they say we give?
He said like type 1 is just going to be like find the directional derivative, and the wording of the problem would be like they give you a point and then like the direct and in the direction of the point, whatever.
Okay.
So it's like you have to find the vectors and like do dot product and all that. Or they'll just give you the vector and you just put it in there.
Okay.
The second one you said would be like, what's the direction of the max rate of change?
All right.
How do you find max rate
Sure.
of change? And the last one was find a direction at this point in which, like, basically the directional derivative is 0 and it's not changing.
Not too terrible. Right. So, welcome to the folks on Zoom. I should start by asking, are there, so you guys have a test tomorrow. Are there any questions from the practice? Is there anything that I can go over? I'm happy to do that. We don't have to, we can totally do other things. Guys, like everyone's cool with the practice test? Cool, good, all right, so. What should we do?
Any tips?
Any tips? So, okay, so. Let's do some practice. All right, so let's say, for example, we have the following function. And we want to find the maximum rate of change at the point 3, comma, -2. Go for it. Let you work on it for a second. Numbers might not be pretty.
They're not.
It's okay. So when you see maximum rate of change, we think what? Gradient. Specifically, this is the magnitude of the gradient. So we're going to find the gradient, which is a vector, and it's just going to be the vector of partial derivatives. The vector fx, fy. So the partial with respect to x is 4x cubed plus 3y squared. The partial with respect to y is going to be 6yx or 6xy, either way you want to write it. So then our well, and then we have to plug in the point. Probably could have picked a nicer point, but it didn't. So at the point 3, -2, our gradient is 4 times 3 cubed is 4 times 27, which is 108. And 3 times 4 is 12, so we get 120. All right, okay. And then 6 times 3 times -2 is going to be what? 18 times -2 is -36. Lovely. So that's our gradient, and then the magnitude of our gradient is going to be just the square root of 120 squared plus -36 squared. And if I were taking a test, I don't know, if you're allowed to use the calculator, it's not hard to simplify this. But if you're not, you are. Simplifying this is not really worth much in the eyes of many people, I feel like. So I would leave it like that unless you're specifically encouraged to do more with it. So yeah, kind of a big number. That's fine. Follow-up question. What's the direction of the maximum rate of change? Well, that's an easy question to answer if we've already done this first part. Be careful though. Whenever someone says direction, I think your teacher's pretty clear, like he does a good job of saying what he wants. But when someone says direction, they mean unit vector. So it's going to take the gradient and divide it by its own magnitude. So our direction here is going to be the gradient divided by its own magnitude, which again, not very nice, but it's going to be, I would probably write it as 1 over the square root of 120 squared plus -36 squared times the vector 120 -36. That's the easiest way we can probably write it. Questions so far? Good. Yeah,
So whatever the rate of change on gradient measurement.
I'm gonna say, I'm gonna clarify slightly, maximum rate of change. Yeah, so the gradient points in the direction of maximum rate of change or steepest incline, or however else you want to phrase that particular idea. Another question someone could ask, this is not a great example, so let's make a new example. So, I'm sorry, my back did not, all of a sudden my back just feels not wonderful, so sorry for all the weird stretching I'm doing, but it just feels not good. Anyway, so let's say we had something like the following. Well, let's see. I'm trying to think of, you said he was going to last. I don't want to be too off base here. So let's say we've got the following function. X comma y is equal to something a little less terrible, like, I don't know, sure, something like x squared plus 4y squared minus 7. And the question we're going to ask is there a direction starting at the point 2 comma 1 in which the directional derivative is equal to 10? It's kind of a good question. And I should follow up with, if so, find it. So the question we're really asking here is, can the derivative be that big or not? So we first have to answer how big the derivative can be, aka what is the magnitude of the gradient. So the gradient here, well, the gradient anywhere, just like before, partial with respect to x, which is 2x, partial with respect to y, which is 8y. So then if we plug in our point, the gradient at the point 2 comma 1 is going to equal 2 times 2 plus 8 times 1, which is the vector 4, 8. Can that, so, all right, that's the right way. Can our derivative be as big as the magnitude of that vector? That's not the way to say that. Is 10 too big? What's the magnitude of this gradient? Well, let's find out. The magnitude of the gradient is going to be the square root of 4 squared plus 8 squared, which is the square root of 16 plus 64, which is the square root of 80, which is definitely strictly less than 10. Right? There's no way that can ever equal 10. So the answer to this question is no. There is no direction where the directional derivative is equal to 10. So the magnitude of the gradient is always an upper limit. Just like, so in a similar way, if we'd asked, is there a direction where the derivative is equal to -10? The answer would be no for the same reason. 10 is the most positive it can be, and the negative of that is the most negative it can be. Sorry, apologies. Square root of 80 is the most positive it can be, so negative square root of 80 is the most negative it can be.
The minimum is did they ask this one the minimum change?
Exactly, yes, exactly that. So in this example, you could say the following. You could say for this particular function, at the point 2 comma 1, the maximum rate of change, or the maximum slope of the surface, or whatever you want to call it, is positive root 80, the magnitude of the gradient, and the minimum rate of change is negative root 80. Because essentially all you're doing is you're standing on the hill, and instead of looking in the direction where you're traveling upwards, you're turning around and looking in the direction where you're traveling downwards, and that slope hasn't changed, it's just your perspective of it has changed, and so it's a negative instead of a positive.
I thought for max rate of change, we put the gradient over the magnitude, but this is the-
We don't, so there's two different things, so let's just speak very generally here. So when you're talking about a function of x and y, the maximum rate of change is the magnitude of the gradient at whatever point. It's just the value, it's the number. On the other hand, the direction of maximum rate of change is the vector that you're in the direction you're traveling in. But again, we always normalize or unitize it. So we make it a vector of magnitude 1. So you take your gradient vector and you divide it by its own magnitude. That's the difference. And then just to kind of go along with what Eric was asking, if instead they asked for a minimum, it would be the negative of your magnitude of your gradient. If they asked for the direction of the minimum rate of change, you would also just do the negative. You would find it to be the negative gradient divided by its own magnitude. Because again, you're really just turning around and going in the opposite direction. What if on the other hand, oh yeah, there's two ways of asking this next question too. So let's say we have another function, xy is equal to, I'm trying to come up with something that's slightly more interesting than just powers of x and y, but I feel like we don't need to be interesting, we just need to be. So I'm always like, well, make it fun. Let's say we have something more like this. 2x cubed plus 5x squared y minus 6y. Sure. And we want to find the, sorry, let me see how to see the directional derivative. This pen's dead. At the point 1 comma, gosh, all my pens dying. At the point 1 comma 3 in the direction of the point 5 comma 2. So there's something to be careful about here. So make sure that when you're finding a directional derivative, you're very, very thoughtful about if they're giving you a point which you're traveling to, or a vector in which you're traveling in the same direction as. So in this case, we're going to find the gradient, of course, because your directional derivative is always equal to your gradient dotted with your direction vector. U should be a unit vector. So let's find U first. So the direction we're traveling in is starting at the point 1, 3 and ending at the point 5, 2. So you could say from the point 1, 3 to the point 5, 2, the vector that gets you there is 5 minus 1, which is 4, and 2 minus 3, which is negative 1. But then that's not a unit vector, which is why I called it V instead of U. So the unit vector we're going to use is just that vector 4, negative 1, divided by its own magnitude, which is the square root of 16 plus 1, which is the square root of 17. So that's our unit vector, which you can write in like 3 different ways. And then our gradient, well, again, just like every time, the gradient is going to be the partial with respect to x, so that's going to be an 8x squared plus a 10xy. And then the second component is going to be a 5x squared minus 6. I think. I said, let me double check here. Oh yeah, wow, brain, yeah, sorry, good call. the 6x squared. Let's double check the rest of it now. Derivative here is 2x times 5 times y. Yep, 10xy. And then the other part's going to be derivative that's 0, derivative that's 5x squared. Yeah, thank you. So then if we plug in our point, our gradient at our point 1, 3 is going to be the vector 6 plus 10 times 1 times 3 is 36. Again, we're getting a 36 again. Didn't plan on that. And then if you plug in 1 here, we get 5 minus 6, which is -1. So we're going to dot these together. So the gradient of f dotted with u is going to be 36 times 4 plus -1 times 1, -1, still divided by that square root of 17. I kind of personally, when I'm dotting these vectors together, that dividing by the magnitude there, just do that at the end. Do the dot product of 4 -1 with 36 -1, and then at the end divide by whatever the magnitude of that unit vector is. So 4 times 36 is 144 plus 1 is 145 divided by the square root of 17. The numbers, hopefully your teacher will give you nicer numbers because he's thought about this test more than I have thought about these numbers I'm making up, but the process is still the same. You're finding gradients, you're dotting them with unit vectors. A question apparently that he likes to ask is, for the same one, sure, why not, same one. In what direction is the directional derivative going to be 0? Yeah.
Is that the same?
Yeah, so we could say that there's like, yeah, there's a lot, that's the hard part, trying to hit the, there's a lot of ways you could say this, the same thing. You could say, in what direction are we traveling perpendicular to the gradient? That's also what you're saying. Or in what direction are we traveling along a level curve? Also the same thing. So all these things mean that the height that your surface, your height is not changing. You are staying at the same height. Your height isn't changing. Your derivative is 0. The nice thing about this is it's relatively easy to find because the easiest way of thinking about it is just we want a vector u that is perpendicular to the gradient. And for vectors in 2 dimensions, it's pretty easy to find perpendicular vectors. If our gradient is equal to the vector 36, -1, all you have to do is essentially change the order of the components and change one of their signs. So you could say that the vector u is either the vector +1, +36, or you can pick -1, -36. And then of course, since we said we wanted a direction, we want to find a unit vector, meaning we should take this and then divide by its magnitude, which is again the square root of 145. So, well, that's not right. How did they come up with that bonkers number? It's not the square root, it's square root of 36 squared plus 1 squared, which is a terrible thing to do, but it is what it is. So every time, if you're being asked for a direction, you should always be thinking, I need to divide by the magnitude of that vector. Erica.
So when we find the max rate of change, we're not using the directional derivative formula.
Correct.
We're just finding the magnitude, like that first part.
You're just finding the magnitude of the gradient. Right.
And then we have the direction. When it's asking us to find it in that direction, we get the gradient and then divide it by it.
Correct.
And then when, I'm just trying to.
No, you're good.
A lot of stuff.
Yeah.
And then when it asks for the, I'm just trying to figure out what's not the difference between all of them, but.
Well, so they're all super related, is the thing. So the thing is, when you're finding the direction that's the maximum rate of change, we originally talked about it using the directional derivative. So if someone asked you, and again, I don't want to say this too much because you don't really need to know this. I mean, you do, but you don't. If I said, what is the direction of the max rate of change, well, what we're doing here is just trying to say, okay, great, maximize this. Maximize the directional derivative, which is equal to the gradient dotted with the unit vector. But one way of calculating a dot product, which we don't usually do, because it's usually a pain in the ass. But one way we calculate the gradient is, sorry, the gradient, not the gradient, the dot product, is it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So magnitude of the direction vector u, well, it's the direction vector, so what's its magnitude? 1. And what's the biggest cosine of theta can ever be? Also 1. So the biggest this directional derivative can ever equal is the gradient of f's magnitude times 1 times 1. So the biggest the directional derivative can ever be is just the magnitude of the gradient. And that's going to be the case when this angle theta is what? What angle do you need for cosine to equal +1? 0. So what you're saying here is you've got your gradient vector and your direction vector. But what we're saying really is that you get the maximum rate of change when the angle between these two vectors is nothing, or in other words, when they point in the same direction. So that's why we say that the direction of maximal rate of change is the direction of the gradient vector. They point in the same direction. The only difference is u is the gradient divided by its own magnitude, because we have to make it a unit vector. So that's why we're getting what we're getting, because really you do have to point in the same direction as the gradient to have a maximum rate of change. I think so. Trying to remember, did you say there was one other one? I don't remember what it was. I think that's kind of it. Yeah.
I had a question about, he has an example that has a f of x, y, and then he gives us a point, and then he gives us a vector.
Okay.
And he says like find the direction of the.
Okay.
But at the end he asks them,
Yeah.
I think that's what
I believe you. I'm just, which one is that? Okay. Maybe adds them. I'm curious. Not that we can't do that. I just, yeah, I'm not. Let's find out.
Yeah, find the directional derivative at point in direction vector v. He gives a point and then the vector,
Sure.
and then it's 1 plus 2x squared of y. And the point is 3, 4, and the vector is 4, -3.
So the function is 1 plus,
2x times the square root.
is it 1 plus 2x all in parentheses times the square root of y?
Yeah. Or no, sorry.
It's all right.
2x, yeah.
So it's 1 plus 2x times the square root of y.
Yeah.
Okay.
And then the point is 3, 4.
Okay.
And then the vector is 4, -3. And he gives us like steps, but at the end he subtracts them.
And what's he asking us to do specifically here?
Find the directional derivative at point in direction vector.
So find the directional derivative of this function at the point 3, 4 in the direction of, so instead of saying v equal to 4, -3, I'm going to say u equal to 4, -3 divided by 5, because that's the magnitude of that vector. So here's what I think we're supposed to do, but so currently I'm not seeing why we're adding yet, but I haven't done the problem yet. So let's take a look. So I'm trying to find the directional derivative. I'm first going to find the gradient. So I might rewrite this just a tiny bit. I might rewrite it as f of xy equal to 1 plus 2x times y to the 1/2, just to make it easier to see how to take the derivatives here. So gradient of f is the partial of x, partial of y. So the partial with respect to x is going to be just 2y to the 1/2, if you prefer 2 times the square root of y. And the partial with respect to y is going to be 2 times x times 1/2 y to the negative 1/2. 2 times x times 1/2 y to the negative 1/2. And it might be worth our while to simplify this just a tiny bit to make it easier to plug things in. If I simplify this, I might write this as 2 times the square root of y. I might write this part as canceling the 2's and write it as x divided by the square root of y. Feel free to ask questions along the way here. Got it. Then if we plug in our point, then things are not going to work out super. No, they're not. No, they're going to be okay. So at point 3, 4, our gradient is going to equal 2 times the square root of 4 and 3 over the square root of 4, which ends up being 2 times 2 and 3 over 2. There's our gradient. Oh, I think I might know what you're saying, but I'm not 100% sure. So then to calculate the directional derivative, we're going to do the directional derivative is just going to be our gradient dotted with our unit vector. So that's going to be the component. Well, in fact, let's write it out. It's going to be 4 3/2 dotted with 4 negative 3 times 1/5. Or you can write that as 4/5 negative 3/5. I don't particularly care to. So here's what I think you might be saying. At this stage here, we do the dot product. When we do the dot product of two vectors, we multiply the first components together. So I mean 4 times 4, and then we add and we multiply the second components together. And we add 3/2 times negative 3. And then all of that gets multiplied by 1/5. Is that what you mean by the adding part?
I wrote down 16 over 5 minus 9 over 10. Equal to 23 over 10.
Sure, that's right. Yeah, so here's what we've got. I'm just doing it in a very, very slightly different way. I've got 16 here minus 9 over 2. So I've got 16 minus 9 over 2 times 1/5. And 16 minus 9 over 2, I'm going to rewrite that as 32 over 2 minus 9 over 2. So that's 32 over 2 minus 9 over 2 times 1/5. 32 minus 9 is 23. 23/2 times 1/5 is 23/10.
It was like the equation of direction of the derivative was equal to the partial of x in xy and a plus fy.
Let me see. I think I know what you're saying, right? Totally, yeah.
So how does that correspond with the formula that we now?
Right. So here's what that's saying. So very, very generally, if you're saying the gradient is the partial of x. Let me look at it one more time. Yeah. At the given point, x comma y, and your partial is like the y at the given point, x comma y. And your unit vector u is maybe written as AB. So in this particular problem, our gradient of f was 2 root y, x over root y, and then our gradient, sorry, you can't do that, evaluated at the point 3, 4 was 2 square root of 4, and then 3 over the square root of 4. Just plugging those points in. That's what that is right there. That's what that is right there. And then our unit vector, I was writing it as the vector 4 negative 3 times 1/5. But if you prefer, you can write this as 4/5 negative 3/5. And then the idea is we're going to dot these two vectors together. And when you dot these two things together, so in the general format here, the gradient of f dotted with the vector u is just that times that plus that times that. So it's going to be your fx at xy times a plus your Fy at xy times b. Or in this particular example, our gradient dotted with our vector u is going to be 2 times the square root of 4, which is 4, times 4/5 plus 3 over the square root of 4, which is 3/2, times negative 3/5. So yeah, it's the same thing.
And then,
Go ahead.
when it's asking for the maximum rate of change, that's normally when we'll get two values, like a vector and the directional derivative.
So I'm gonna say 3 things. So you have the directional derivative is a derivative. Directional derivative is some derivative. So it's got some first component, some second component. Sorry. Wow, I just said the totally wrong thing. I apologize. That is so not true. I'm such a liar. Wow. I kind of hate myself right now. Apologies. So directional derivative is so you hear directional derivative. Think about 17a for a second. If you're finding a derivative, what are you finding? Rate of change. And specifically as a graphical interpretation, like for a function of like a usual function graphed in xy plane, the derivative is just the slope of the tangent line. But it's the slope, right? It's the numerical value that is the slope. So directional derivative or just derivative is going to be a value. It's going to be a number. So it's going to equal some number. Could be positive, could be negative. The max rate of change is also some number, but specifically is the magnitude of the gradient. And then the thing that sounds kind of the same, but is a little bit different, is the direction of the maximum rate of change. That is going to be the vector gradient of f divided by its own magnitude. So we'll do an example. We'll go ahead. Yeah.
So when it says slope, we think direction derivative.
Correct.
But if they say steepest slope, do we go macro?
Correct. Yes. So yeah. So that's in fact directional derivative, slope in a particular direction. Max rate of change is maximum slope. And direction of max rate of change is the direction in which you maximum slope.
And just to clarify, the third one, direction of the max rate of change, that can be like, find the max rate of change at point 3, -2, like.
But it's specifically it's asking for the vector, not for the
Right, but that's just how they would like ask. you.
Yes. Yeah.
And we also talk about like what information they would give us for each one, like first one, they would give us a point in a vector.
So let's look at an example. So well, yeah. So in fact, so the examples I've been giving have all been starting with a function, right? But there's definitely so someone could give you not that information, give you different information. So let's see. I don't want to think about this for a second. So someone could give you something like what he is giving you on the practice exam, where you've got some function of x and y, and they haven't actually given you all the things. But they didn't tell you what the function was. They've just told us that the partial derivative at some point, let's say, I don't really care what the point is. Let's say it's 19 comma -3, just to be weird about it. That partial derivative is equal to 4. And the partial derivative of the y direction at the same point is equal to, I want to be sure, is equal to 5. So then we could say, all right, at the point 19 comma -3, well, first I'm going to ask, before we get too involved here, First question. What is the maximum rate of change? I think that's a pretty okay question. Just think about what the answer is or write it down if you want to. You don't have to write it down. All right. That. I should have been more specific, but I feel like it's clear. Max rate of change at the point 19 comma negative 3. Guess that wasn't clear. Okay. So max rate of change, we know is just the magnitude of the gradient. Our gradient vector is the vector fx, fy. So our gradient vector at the point 19 negative 3 is 4, 5. And its magnitude is just the square root of 4 squared plus 5 squared, which is the square root of 41. So that is the maximum rate of change. What is the direction of the maximum rate of change? So when they ask for a direction, we know that the answer is a vector, specifically a unit vector. So we're just going to take our gradient vector and divide by its own magnitude. So in this case, that's going to happen to be the vector 4, 5 divided by its own magnitude, which is the square root of 41. Which you could write, I would probably write it like this. 4 over root 41, 5 over root 41.
Did you do it where you have like the 4 comma 5, the arrow?
Totally, yep. You can do it like this. You could bring the 1 over root 41 out in front, right? There's a lot of different ways you could write this. All of them should be fine. Yes, the dividing by, so the process of dividing a vector by its own magnitude is the process of normalizing it. That's what it means to normalize a vector. To me, normalizing a vector is just say I want a vector that's in the same direction, but with a length of 1. So we divide by its own length. And then thirdly, we could ask the question, what is the slope of the surface in the direction of the point 25 comma 7. Sorry, not 7, 5. Apologies. Okay, so to find the slope of the surface, aka the derivative, aka the directional derivative, we need our gradient, which we already have, and our vector, which we're going to find. And I guess, again, I know I'm not being extra super clear. What is the slope of the surface at 19 comma 3? Sorry, negative 3. Because that's the point we've been working with in the direction of the point 25 comma 5. So we need to calculate the following. We already know what the gradient is. The gradient is just the vector 4, 5. We have to find our unit vector. So we know we're starting at the point 19 comma negative 3, and we're ending at the point 25 comma 5. And so our vector that gets us from there to there is, let's see, 25 minus 9 is 6. 5 minus -3 is 8. So our unit vector is 6 divided by the magnitude of this vector, which is 10. And 8 divided by the magnitude of that vector, which is also 10. Because it's a 6, 8, 10 triangle. Or you could, square root of 6 squared plus 8 squared is the square root of 100, which is 10. So that's the vector we're going to be dotting with. We're going to be dotting with the vector 6/10, 8/10. Or maybe I should have reduced those fractions, but I didn't. So then I've got 4 times 6/10, which is 24 over 10, plus 5 times 8/10, which is 40 over 10, which adds up to 64 over 10, or 6.4. Or some other fraction that's smaller than that. So, I want to say one more time. The only one of these three things that's a vector is the direction of the maximum rate of change. The other two things, which is the maximum rate of change, is a number or a scalar, and the directional derivative is also a number or a scalar. Another vector I could ask for, though, would be the other question that's kind of on the test is what direction could we travel in so that our rate of change was 0, so that our height didn't change. And that's where you essentially just find something that's perpendicular to the thing, the upside down triangle thing. Wow, the gradient, yeah. It's called a nabla, I think, and it's kind of weird. I'm not a fan of the name of the upside down triangle. Right, so you could find another vector, say v, that is perpendicular to the gradient. In this case, my gradient being 4, 5, it's not hard to find a vector v. You can say that v is the vector -5, 4, and then divided by its own magnitude, which is 25 plus 16. And that vector, -5 over root 41, 4 over root 41, is perpendicular to the gradient. It's the direction we travel to stay on the level curve. There's a lot of different ways of saying the same thing. Okay. One more time. So the way I'm always, if I'm ever trying to find a vector that's perpendicular to another vector, I'm taking that original vector, and so I'm kind of taking a shortcut, to be perfectly honest. What I'm really saying is, okay, my vector v, I want my vector v to be perpendicular to the gradient, which happens to be 4, 5 in this particular example. So I'm going to say the vector v, you can call it a, b if you want. So if two vectors are perpendicular, their dot product is 0. That's kind of the great thing about vectors that are perpendicular. Their dot product is always equal to 0. And so if we say, okay, well, I'm going to take the dot product of my gradient and my vector v, it's going to be 4, 5 dotted with ab. I get 4a plus 5b, and I want that to equal 0. So then you can do this kind of any way you want. I would typically just say, well, 4a equals -5b. So then I'm going to say that a equals -5 and b equals +4, or whatever version of that you like. Which I think I said slightly oppositely. That's fine. No, I didn't. So yeah, or you can actually solve and say a is -5 fourths b, and then you can let b equal 4, and you get a equal to -5. So then our vector is going to be -5, 4, but I then need to normalize it by dividing by some magnitude. So my actual vector is going to be 1 over the square root of 41 times the vector -5, 4. But the shortcut is just to say, take the vector you want to be perpendicular to, change the order of the entries, and change the sign of one of them. So you could have said -5, 4, or you could have also equivalently said 5, -4 would have worked just fine as well. So that's kind of the fast way of doing it. But the long way of saying, oh, if we want vectors that are perpendicular, you just want their dot product to equal 0. Okay. More questions about this particular topic? Or should we move on? Oh, yeah, question. Because we've been asked. So like, I think, so for like, I mean, I think the question on the practice exam was. Oh, yeah, you want to make sure that you avoid climbing at every point. So when I read this question the first time, I misinterpreted it. I thought that meant just that the derivative couldn't be positive. So I was like, well, the derivative could be negative and that'd be fine because we're not, but really they meant to be not climbing or descending. So if I want to be not climbing or descending, I want to be, right, if I'm walking on my mountain, I'm going for a hike, I'm just trying to like travel on a nice level curve where I'm not going up or down. And that's the case, you want your derivative to be zero. And the way for the derivative to be zero, well, again, the way we calculate the directional derivative is equal to the gradient dotted with the direction you're traveling in. And so if we want that to equal zero, well, if the dot product's zero, the vectors are perpendicular. So this exactly means that the gradient of f and the vector u are perpendicular. So that's kind of why we were doing it, because the question was leading us in that direction. But you, again, like we've seen, you can phrase it in any number of ways. Okay, that's fine. Other stuff about this. Yeah.
I get what you're saying.
Uh-huh. Uh-huh. So we only want to switch one of the signs. Let me go back. Sorry, I'm trying to look for the example we're talking about. So for in that example, the gradient was 36 negative 1. And so to get a vector, now there's lots of potential answers, but one vector that's going to be perpendicular, I'm going to switch those and I'm going to change one of the signs. So you can either change -1 to +1, or it would also be equivalent, although it would be in the opposite direction, to have the vector -1, -36. Well, so they're not in the, so here's graphically what's happening. So the idea here is that you've got a vector. Here's your vector. Let's say it's the vector, terrible, I don't like it. Let's say that this is the vector 36, 1, -1. Even though it doesn't look like it the way I've got. I want to find a vector that's perpendicular to it. I want to find a unit vector that's perpendicular to it. You really only have two choices if you're trying to live in the same plane. You have this vector. And maybe this vector is the one that is +1, +36 divided by the square root of the magnitude. Or sorry, the magnitude, which is some terrible number. 36 squared plus 1. Or you have the vector that points in the opposite direction. And when vectors point in opposite directions, they are negatives of each other. So the negative of this vector would be -1, -36 over the square root of the magnitude. So that's why I've said you can take your vector and you can switch the order. We switch and we get +1. Sorry, -1, +36. I switch the order and then I can change one of the signs. I can either go +1, +36 or -1, -36. And that'll get me there. Because when you dot this vector with this vector, you get 0 because you get 36 plus -36. When you dot this vector with this vector, you get -36 plus 36. Either way, you get 0. But that's what the switching of the signs is. The switching of the signs gets us to a place where the dot product form is being 0. Very, very generally, we can say that if your vector is AB, then this other vector, negative BA, or B negative A is perpendicular. Because the dot product is A times negative B plus B times A, or A times B plus B times A. Yeah. Okay. Other vectory question. I know it's been a while, right? The vectors are like, way back there, like, oh yeah, we talked about vectors and stuff way back when. The other stuff we've been talking about for what feels like weeks, so I feel like it's a little more fresh in our minds. Sure.
I'm happy to solve for them.
Yes.
And they all when I'm solving.
Okay, sure. I would be willing to bet you're probably gonna see, I think I know what you mean, but
Yeah, I have an example.
Sure.
The matrix.
Okay.
Is A2,
okay.
and then the eigenvalues is 6 and -6.
Oh, there you gave us guys. Okay. Oh yeah, I definitely saw this one in the. So let's talk about how to find the eigenvector. Would anyone like to see how we find the eigenvalues first? Are we cool? I can double shut up. Okay, I think we're good. All right, so to find the eigenvectors, there's two ways you can go. You can go the way I like to go, which is the following. And either way should be totally valid, but I'll show both ways. So one way is to solve this. Solve A times your unknown eigenvector equals a lambda times your unknown eigenvector. So let's see the work here, and then we'll talk about the other way, which is probably the way you might be thinking of it. So I'm going to do -2, 4, 8, 2 times the vector xy equal to lambda. Let's do for lambda equal to 6 first. So we'll do lambda equal to 6. 6 times the vector xy. Most of the time when you do this, you should only need one of the equations. Meaning, I'm not going to write down both -2 times x plus 4 times y equals 6 times x and 8 times x plus 2 times y equals 6 times y. You could, but you usually don't need both. You almost never need both, to be honest. So I usually just use the first one, unless there's a good reason to use the second. So -2 times x plus 4 times y equals 6 times x. And then typically we don't even really isolate y. We typically just get something times y equals something times x. So adding 2x to both sides, I get 4y equals 8x. I might divide both sides by whatever greatest common factor they have. So I have the smallest possible integers. So dividing both sides by 4, I get y equal to 2x. And from there, we're going to say that our eigenvector is, well, if x is 1, y is 2.
So do you always need x?
Typically, yes. But really, you can pick anything. So any multiple of this is also a valid answer. So you could have said, I don't like 1. It's not my favorite number in the world. I'm going to pick x to be 3 and y is going to be 6. And that is also a completely legitimate answer. The default that people usually go to is trying to make it so all of the entries are the smallest integers possible. So while it's totally also valid to say that you could pick 3, 6, we don't because we'd like to reduce that. It's also totally valid if you actually, well, you could pick, say, x equal to 1/2 and y equal to 1. We don't like that either because we got fractions. They're both totally valid answers, though, and should get you full credit. So the gist here is that when you get to this point where you have y equal to something times x, or 4y equal to something times x, you just have to choose. And the only thing you can't choose is you can't choose both x and y equal to 0. So I'm going to make it extra super clear. 0, 0 is never an eigenvector. If you're getting 0, 0, go back to the drawing board. There's something weird happening. You can certainly get one of the coordinates to be 0, and if that's the case, the other one is whatever value you want it to be. Typically, it's 1. So let's just point out the other way you could solve this, in case you don't like doing it this way, is to solve a minus lambda I times your unknown eigenvector equal to the 0 vector. That's the other typical way of doing this. So in that case, we're going to have -2 minus 6
4, 8, and 2 minus 6 times xy equal to 0, 0. And what should happen most of the time with this is both rows should be multiples of each other when you simplify them. So if I look at this just to see that, I have a -8, 4 and an 8, -4 times xy equal to 0, 0. And hopefully we can all see that these are essentially the same equations. -8 times x plus 4 times y equal to 0 is pretty much the same thing as 8 times x minus 4 times y equal to 0. And either way, we're going to get back to the same place we got to before. The first equation, -8x plus 4y equal to 0, leads me straight back to 4y equal to 8x, and then y equal to 2x. So doing it either way is totally fine. Do whatever is more comfortable for you. Sure. Yes, and you should. So I will say it does, well, actually, no. So yes. But here's what I'll actually say. So let me just make up something else to be kind of, let me make something up to show you what I mean. So let's say that we did all this work and we got we were doing the work, and we ended up with the following. So we got to a place where we had, sure, I'm going to say 3y equal to -2x. That's what we got after doing all the work to find the eigenvector. So you can either solve for y and say y equals -2/3 x, or not. So I would love for all of you to write down what the eigenvector would be for this. You can write, and there's lots of right answers. Try and write the answer you think I would write. Okay. The answer I would write would be x equal to 3, y equal to -2. The reason I'm choosing that specifically, I'm actually really looking at this and just saying x is that coefficient, y is that coefficient. Or you can look at this and be like, well, the number I'm going to pick for x to make things nice is x equal to 3. Because then -2/3 times 3 gives me a -2 for y. Now, there's totally plenty of other valid options. You could totally say that your eigenvector is, although I don't like it, but it's totally fine. So your eigenvector is x equal to 1 and y equal to -2/3. Now, there's a good reason I like this choice. The reason I like this choice is because when I start trying to draw the phase portrait, instead of having to actually graph the line y equals -2/3 x, do the following. I'm going to go through the vector 3, -2. Specifically, that vector starts at the origin and goes over 3 and down 2. So the line that goes through, where'd my ruler go? I think I hid it in my bag somewhere. The line that goes through the origin and that point is the line that you want. I totally did. That's disappointing. Anyway, it's not that important. I thought it was. Oh, there it is. It's hiding from me. Plain sight. So here is your eigenline. So here's your eigenline going with lambda 1. I don't know if lambda 1's positive or negative because I just made stuff up. And then in a similar sort of way, if your other eigenvector equation ended up getting you something like, I don't know, 5y equal to 4x, you could, right, so this is for v1, for v2, you would end up saying, well, I'm going to pick x equal to 5 and y equal to 4. Or you could do the work and say, okay, y equals 4/5 x, and then get x equal to 5 and y equal to 4. Or x equal to 1 and y equal to 4/5, but nobody wants that, right? You don't want to do that because it's harder to graph that. It's much, much easier to be like, okay, if I'm going to plot that point that eigenvector kind of goes through, I'm just going over 5 and up 4. So that's another reason why it's nice to write the eigenvectors like that, where the entries are actually both integers, because it makes it really, really easy to find where on your phase portrait you want your lines to go through. Now, what's that? No, you go ahead. It's important that you know, so let's say we actually did have the eigenvalues. Let's pretend that let's pretend that lambda 1 was 3 and lambda 2 was -6. So then I need to know which one goes with which because my arrows point certain directions based on that. So if lambda is positive, then the direction is away from the origin on that eigenline. And if lambda is negative, then the direction is towards the origin along that eigenline. Can't ever cross an eigenline with your trajectory. Kind of cool. But the thing is, right, the eigenline basically says once you're on that line, you're traveling in that direction. So you can't just cross over it because once you hit that point, you're stuck going in that direction. So if you start somewhere like here, you basically look at what eigenlines you're between, and then those kind of dictate which way you travel. So I'm going to travel that way, but then I'm going to push that way as well. So I'm probably doing something like that. For a saddle like this, you always, with one exception, end up going in the direction of the one that's away from the origin. So no matter where you start, with one exception, you end up saying, oh, I'm just going to go away like that. Or if I start, like way over here, I'm going to be like that. The only exception is if you happen to start on the eigenline that is the one with the negative eigenvalue, then you go straight in towards the origin. Like that. That was a question. Or a comment, yeah. Either one. We'll look at the example in just a second.
If you ask for trajectories, like 4 trajectories, you just draw them, or do you have to be like, I'm choosing?
No, just draw them. He really just wants you to be able to be like, I know it looks like this, this, or this. And really, your trajectories are the following. If one eigenvalue is negative, one eigenvalue is positive, you've got this thing where you essentially go towards the direction where your eigenvalue is positive. Right, so all my trajectories maybe start somewhere here, but they eventually go that way or that way. It just depends on which side of the other eigenvector you're at. If both eigenvalues are positive, you're going out, no matter where you start. So like if you had something like this, but both my eigenlines, both of them had positive eigenvalues. That's a good question. Sorry, I'm just thinking about something here. Any trajectory you draw, you're going to go further out. Now, I think there's some, in fact, I was looking at his, yeah. So like, for example, I know you can't really see these graphs particularly well, but you've seen them all probably on your practice test. So if you look at this one, like this one here is the saddle-y one, I think. Yeah, and these ones here both kind of go out. But here you can kind of see, right, it looks like there's an eigenline here and an eigenline here, but clearly you're going like that way, right? All of them are going in the direction of probably the eigenvector that has the larger positive value. That's typically the one that dominates your phase portrait. So if you happen to know both values, you might try and draw trajectories that tend towards the bigger one versus the smaller one. But really, I think they're just looking for you. Do you know they all go out, all go in, or for the saddle, inward and outward? I think that's what they're really looking for when they ask that question. I don't think he's going to have you draw any spirally things. I feel like he said that.
Yeah, there's like no complex idea.
Yeah, which is, I mean, kind of too bad, but not too bad if you're a student. It's too bad from a. It's I think they're fine. But there was so Erica, real quick.
Oh, it's on another.
Okay, so the one thing I want to address is, so I'd be willing to bet a decent amount of money. You might see a matrix like this, where you got a 0 in either the upper right-hand corner, or you've got a 0 in the lower left-hand corner. If that's the case, a couple things are going to happen. Thing one, the eigenvalues are super easy to find. So in either of these cases, here we know the eigenvalues are 3 and 5. Here, we know the eigenvalues are 2 and -1. So right away, here you know you have an unstable source, or I should say an unstable node, which is a source. Your eigenvalues are positive. Here you know you have a saddle because your eigenvalues are opposite signs.
Would this apply to if the 0 was in the 2 or the -1 or the? 5?
No, the 0 has to be in the upper right-hand corner or in the lower left-hand corner, or in both. So you could also, so I should also point out, you could also have a purely diagonal matrix where you had something like -5, 0, 0, -6. And here your eigenvalues would be -5 and -6. And you'd have a sink or a stable node. But yes, it's only true if you have a 0 in the upper left-hand corner or lower right corner. Sorry, upper right-hand, lower left-hand. I should just say not in the diagonal, right? So this is the diagonal of the matrix. And if one of your non-diagonal entries is 0, then the eigenvalues are always the diagonal entries. And it's actually really easy to show. If you actually just try to calculate the eigenvalues here, if you're taking the determinant of a minus lambda I, look what happens. I'm going to do the determinant of 3 minus lambda, 0, 4, 5 minus lambda. I want you all just to watch this for 1 second. If I take this determinant, look what happens. I've got that times that. So 3 minus lambda times 5 minus lambda minus that times that. 0 times 4 equal to 0. Now don't be a sucker. Don't do more work than you need to do. You're already done. All you have to do is not multiply this out. Say I've got 3 minus lambda times 5 minus lambda equal to 0. Oh, that means lambda has to be 3 or lambda has to be 5. Don't do too much work. So if you see a 0 here or a 0 here or a 0 in both spots, your teacher might be cool with you just saying, you know what the eigenvalues are. But even if they're not, it's a very minimal amount of work to find the eigenvalues. Just don't do more, don't multiply it out unless you have to. The other thing I will point out is if this happens, which it's a pretty good bet, you'll see one like this. Your eigenvectors usually do something kind of janky. So I'm going to find them the usual way I find them. I'm going to take this matrix. I'm going to take that matrix, 3, 0, 4, 5. I'm going to multiply it by my eigenvector and set it equal to my eigenvalue times my eigenvector. One of them is usually fine. One of them is usually weird. Fine's maybe an overstatement. So I've got this. And I've also got the other one. 3, 0, 4, 5 times my unknown eigenvector equal to 5 times my unknown eigenvector. This is for lambda equal to 3. This is for lambda equal to 5. So typically, I like to look at the first row's worth of equations because it's just where my eyes go first. So looking at the first row, we have 3x plus 0y equals 3x. And that tells me absolutely nothing. X can be anything. That doesn't help. So I move on. So then the other equation, 4x plus 5y equal to 3 times y. Oh, that tells me something. I can isolate y and I get 4x equal to -2y or 2x equal to -y. So I would probably pick x equal to 1. I hate this actually. I would probably write it as -2x equal to +y just because that's how I would usually do it. And then my vector would be x is 1, y is -2. On the other hand, over here is where things are a little bit weirder. You have to be more careful about what happens. The first equation is 3x plus 0y equals 5x. And that actually is enough information to know what's going to happen. You guys have your test right after this? No, today's Tuesday. I'm sorry. I'm used to having this class on the day the class was on. So I was like, oh, we have a test right after. So here, that's enough. What does x have to be? X has to be 0. You can do the math, right? You can subtract 3x from both sides and say 2x equals 0, so x equals 0. And then, since we know that 0, 0 cannot be an eigenvector, y can be anything but 0. So you could pick something weird like 0, 6 as your eigenvector, but we usually make the choice of 0, 1 as your eigenvector. You're welcome. So yes, if you end up, so, and that's the thing, when you have one of these things where you have a 0 there or a 0 there, this kind of eigenvector always ends up showing up. The same would be true if you had the other kind of thing, like we looked at our 2, 5, 0, -1 matrix, and I was trying to find the eigenvalues for either, sorry, the eigenvectors for 2 or for -1. If I'm finding it for 2, look what happens. I end up with 2 times x plus 5 times y equals 2 times x. The 2 x's cancel and you get 5y equal to 0, which means y is equal to 0, which means x can be anything you want. So the eigenvector is 1, 0. That'll always happen if you have one of these types of matrices. And it typically won't happen if you don't. So. Sorry, people left. I felt like class over. Go ahead. Sure. So looking at this one here, sorry. Yeah. So looking at the previous example for the matrix, A equals 3, 0, 4, 5, which you should think of as really, that's a system of equations, right? This really means dx dt equals 3x and dy dt equals 4x plus 5y. It's important that you can go back and forth between this and this. So if I was graphing the eigen or the phase portrait in general, sorry, let me write these down real quick. So for lambda, and it's good to label this, I would say that lambda 1 equals 3, and my v1 was 1, -2. And for lambda 2 equal to, what was the other one? 5? Yeah, 5. My v2 is 0, 1. Okay, both eigenvalues are positive, meaning we know everything's gonna be pointing out away from the origin. It doesn't just mean up, it means out. So, right, if you're below, you're out, down, if you're above, you're up. Yeah. And so on this line, and I would use a different color if I had a different color, if I do. So on the line 1, -2, I'm just going over 1 and down 2. That's the easiest way for me to graph the eigenline. I feel like he called it something slightly different on your assignment or on your practice final here, practice midterm. Sorry, I'm just curious. No, I don't know. Okay. Include the lines corresponding to both eigenvectors, which we've been calling the eigen. Same idea. So my line there, over 1, down 2, which is the line y equals -2x. I just don't think you need to actually find that. If you know what the eigenvector is, you can draw it. Now be careful. Don't do what I would normally do when I draw a line, which is put arrows at the end. That's what I usually want to do when I draw a line. It would be fine in this particular case since our arrows do need to point outwards, but don't just draw the arrows on there. Like, oh yeah, these ones go outwards, so they go like this. The other eigenvector is the eigenvector 0, 1, which is just over 0 and up 1. So that's where it ends. So it's really just the y-axis. And again, we're pointing outward, so we're pointing like that. And if I had to draw a trajectory, which is never my favorite thing, if I had to draw a trajectory, I'm going outward, and I think I'm going more this way. So it's probably like, I don't know. Trajectories are not my best. I won't lie. But we're probably going more like that. I don't actually know though, because again. I wouldn't think so. I mean, you could ask him, but you could ask him to like, you could literally ask him, like, if you had something like this, like, which way did they go? Now, one thing, actually, we got a minute. Might as well take a look just to know. So they should not be straight. So here's the thing. Here's something to know. The only ones that are straight are the ones that are on the eigenlines. So if you're not on the eigenline, both of these vectors are kind of influencing which way your trajectory goes. So I'm going that way and that way. And again, I don't think I've done a very good job of drawing. But let's take a look just so we can kind of see. So, come on, you do it. So our equation was, again, it was dx dt equal to 3 times x. And dy dt equal to 4 times x plus 5 times y. And if we graph it, scroll down a little bit. And then if we pick a point like over here, like I did, yeah, so the idea basically is if you go forward in time, they're moving away from the origin. If you were to go backward in time, you would be moving towards the origin. Not a spiral though, right? It definitely is a source or an unstable node, even though you've got this kind of curvy motion. Now, I feel like, curious, did I draw something wrong here? No, I don't think so. It just looks like, yeah. Let me see. To pick something over here. Oh, yeah. So you're right. There's your eigenline somewhere around there. Right, the line y equals negative 2x. And so what's happening here is, what I think is happening here is, right, you're kind of getting influenced both by this eigenline and that eigenline. And so over here, it just kind of keeps going that way, that way, that way. It's getting more and more negative in both directions. But yeah, it's not always super clear to me exactly how the trajectories look. I'll be perfectly frank. Yeah. Correct. So the eigenline just points away from the origin if the eigenvalue is positive, in towards the origin if the eigenvalue is negative. And again, the real reason for that is because of how the general solution looks. Right? If you're talking about your general solution is that x of t as a vector is c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. So if your eigenvalues are positive, then these things grow as time goes on and on and on. So your x and y either both get very, very large or both get very, very negatively large, or one of each, but they both are getting larger in some way, either negatively or positively. Whereas if either one of these are negative, then that particular part gets smaller and smaller and smaller as time goes on. So that's why if they're both negative, each of these things get closer and closer to 0. And so x and y both tend towards the origin as time goes on. That's fine. Yeah. Yeah. Right. So first of all, I wouldn't say they're both stable in that case. I would say that the system is stable. Right? Because if one's negative, one's positive, I wouldn't say that the negative one is stable. I would say that we overall have a saddle, which is generally unstable except along the one negative. You're not wrong to say what you're saying, it's just not exactly right. But so yeah, so if both eigenvalues were negative, we had something like, which I imagine he might ask, because like this example didn't have one with us, but like let's say we had an eigenvalue like an eigenline like this where we're going in. Another eigenline maybe like, I don't know, this. Also going in. So if you start somewhere like here, it's not just a straight shot into the origin. You don't just go boom like a straight line. It's supposed to be kind of curved. And again, this is where I'm not like, I feel like the bigger eigenvalue is supposed to be the one that kind of affects it more, but you're probably doing something more like that. Or potentially something more like that. The one word of advice I'll give you when you're drawing trajectories is, what can't we never cross? You can't cross the eigenlines. You can never cross the eigenlines is the one thing I would say to remember. Unless you're already on it, but you're not crossing it, then you're just traveling along. So you can never go from one side of the eigenline to the other side. And if you start not on the eigenline, you can't ever end up on the eigenline. So yeah. Kind of fun. All right, we're out of time. Good luck on your test tomorrow. I hope it goes well. I'll be over and drop in right now. Tomorrow I have office. What time's your test tomorrow? Okay, tomorrow I have office hours from 11 to noon in C class, which is over in the MU, and then from not helpful time. So yeah, from 11 to noon in C class. And during your test and drop in, but that's not helpful. So. I'm sure you're all aware, but I'll just remind you all.